Okay, so welcome back. So now in this video we're going to talk about a specific category of series, or sequences rather. And so let's consider sequences of the type R to the n. And we're going to consider R greater than 0 greater than or equal to 0 and less than or equal to 1. Okay. So now we're going to apply what we learned in the last video to this, to evaluate the limit of this sequence. Okay. So we can use the theorem in the last video to evaluate it. Okay. So what we're going to do is we're going to say, okay, what's the limit as n approaches infinity of R sub n? Well, let's take an example. What if we have 1/2, right? Okay. Well, if we take f of x equal to 1/2 to the x power, and we take the limit of that, let's see. Well, we know the limit as x approaches infinity of 1/2 to the x power equals 0. Okay? So therefore, we know that the limit as n approaches infinity of 1/2 to the nth power equals 0. It must, by the theorem. Okay? Which means that the sequence is convergent. Okay? And it converges to 0. Now, on the other hand, so basically this is true for any value that's less than 1 and greater than 0. But what about 1? Well, in the case that r equals 1, well, then you just get right? Which is just equal to 1, right? So again, 1 to the x power, f of x, equals 1 to the x. And any power, right? Any power of 1 is just 1, right? So the limit as x approaches infinity of 1 to the x equals 1. So we get the same result for 1. So we know that this sequence converges on this interval. And obviously 0, right? 0 to a power is still 0. So similarly, we still have convergence. Now what about if r is bigger than 1? Well, if r is bigger than 1, then f of x equals r to the x, okay, does not converge. It diverges. So again, we can see this by taking the limit as x approaches infinity of r of x, right? And so we could see this, we could take r equals to, let's say, 3/2 to the x power. Okay, well, we can see that the numerator is going to grow faster than the denominator as x goes to infinity. So this is going to infinity, so it diverges. So the function diverges. The limit does not exist. Now, so in this case, we can't use the theorem. Okay? So, but we do know by looking at r sub n, okay, just as the function r of x grows without bounds as n goes to n goes to infinity, the term of the sequence is also going to increase without bounds. So even though we can't use the theorem, we can still see that the limit of r sub n, well, let me do it this way. Still goes to infinity. Okay, so we can still see that it diverges. And so we can still conclude that the sequence r sub n diverges for values of r that are bigger than 1. Okay, so what else can I say? So basically, here's what we have. So for the sequence, for this particular sequence, r to the nth power, we have these three cases. Okay? For r equals, how do I want to write this? So for here, r sub n approaches 0 for r greater than or equal to 0 and less than 1. Okay. R sub n approaches 1 for r equal to 1, and then r to the n approaches infinity for r greater than 1. So now later on we're going to consider the case when r is negative, when r is less than 0. Okay? Now, in the next video we're going to consider more complicated looking sequences and see how we can handle those and see if there's anything else we can do to handle things that look more complicated. And we'll see you then.